All right, section 2 of chapter 5. So chapter 5, we're now going to deal with the last two functions we haven't discussed in the library of functions, logarithms and exponentials. Section 2 deals with exponential functions and their graphs. An exponential function has this form, a to the power x, where a is called the base, since it is an exponential, and x power is called the exponent. The restrictions of which are the power, the exponent, has to be a real number, cannot be imaginary, cannot be unreal, cannot be a complex number. And the base a has to be an integer, has to be greater than 1, and it cannot equal 0. Which means a can be between 0 and 1, and a can be greater than 1. And depending on which one of those two you have as a base, that will dictate what the graph looks like. Examples of exponential numbers are functions. Two to the power x, 1/2 to the power x, 3.57 to the power x, and so on and so forth. As long as it matches, as long as it satisfies this domain, it's good to go. Well, the power x, x can be an integer, it could be a fraction, it could be a symbol, it could be an equation. So your exponent can have any of those conditions as long as it's a real number. What? Graphs of exponential functions. We have two basic graphs here, depending on the base that we're dealing with. If a is between 0 and 1, and if a is greater than 1. The only intercept that exponential function has, the basic one, is it crosses the y-axis at 1. Because anything, when x is 0, anything to the 0 power is 1. So it crosses through there. If your a is a fraction, it's a decimal, your graph looks like this. It goes to positive infinity as x goes to negative infinity, and it goes to 0 as x goes to positive infinity. It's a decreasing function. Now, the smaller the base A is, the steeper it becomes. So the bigger the decimal, the more shallow it becomes. If you think about it, if A equals 1, what would the graph look like? A to any power is what? Is 1. So it'd be a horizontal line. That's why A cannot equal 1. It would be a horizontal 1. That's why it cannot be that. So the if the base gets closer to 1, it gets more and more and more flat. The smaller it gets, the more steep it becomes. This is, let's say, the 0.9 would look something like this. This is 0.9 to the power x. This is 1 to the power x. That doesn't exist. So the bigger the base, the closer it is to 1, the more shallow it becomes, the lower it becomes. On the other side, when A is greater than 1, it's a completely increasing function. It goes to infinity as x goes to infinity. And it goes to 0 as x goes to negative infinity. Same reasoning, same logic. If it's a horizontal line, when A equals 1, so the bigger the number, the steeper it becomes. The closer the number, the more shallow it becomes. So the closer the number gets to 1, the closer it becomes straight. Those are the graphs. There is no x-intercept ever, unless you have a vertical shift. That adds another story. But this is the basic graph. An exponential function is an increasing function that goes on forever and ever and ever. It never stops. All right, let's look at the properties. Remember, the exponential, it crosses through 1, and it looks like that. So the function looks like f of x equals a to the power x. This case, is a between 0 and 1, or is a greater than 1 in this one? Greater than 1, because it's increasing. And a cannot equal 1. The function is continuous. There's no break ever on a function. Is it 1-to-1? What determines 1-to-oneness? Okay, so what would be the inverse of an exponential function? But if you have a graph, it's not easier. No. Well, you can use that. You can go with that. It touches the y-axis once. Which test do we use? Horizontal line test. Very good. Horizontal line test. Because if you draw a horizontal line, it only touches one. That means it's 1-to-1. That means it has an inverse. It's 1-to-1. Very good. What does the vertical line test tell you? Vertical line. I know that, but what does it tell you? It's what it does. It crosses the graph only once. Tells you if it's a function. If it's a function, then it only crosses it once. This is the horizontal line test. And this is the vertical line test. What's the domain? All real numbers from negative infinity to positive infinity. What's the range? No. No. Range deals with which numbers? The y-axis. So you have to ask yourself, can it be negative? Does the graph go below the x-axis? No. Can it equal 0? Why do you say no? Because there's no x-intercept. The only way you can cross the x-axis is if it has an x-intercept. So no. So can it be positive? Yes. So the range is anything greater than 0, as the graph shows. It doesn't cross the x-axis, doesn't have negative, it's only positive. So it's above, so it's y is greater than 0. It's increasing whenever a is bigger than 1. It's decreasing whenever a is between 0 and 1. No vertical asymptote. And it has a horizontal asymptote at y equals 0, or the x-axis. X-intercept does not exist since it never crosses the x-axis. The y-intercept is at 0, 1. So with that, the transformation rules that we discussed in chapter 1 still apply, or chapter 2 still apply. Does not exist, right? So what would the graph of this function look like if we sketched it? Right. Crossing through 1. I said earlier, it always crosses through 1. Example 2. 1/2 to the power x. What's that one going to look like? It crosses through where? And it's a decreasing function.
Less than has to be negative.
It can't be negative.
I mean, although it decreasing.
Right. If it's less than 1, between 0 and 1, it's decreasing. Now, let me show you a reason why. Here we'll have a table of values. Let's just find some points. Here's my x values. This is f of x 2 to the power x. This is f of x 1/2 to the power x. So let's go -2, -1, 0, 1, and 2. So if we had 2 to the power -2, the negative exponent means that we have a fraction. So make this whole thing go on the bottom. So 1 over 2 squared is 1/4. At -1, we have 2 to the power -1. Remember, the rule is this. If you have a negative exponent, you switch locations. Put on the other side of the x-axis. If you have a negative on the bottom, then you bring it up on top and drop the negative. That's what negative exponents mean. If you have a fraction and it has a negative exponent, then you flip the fraction and drop the negative. So these are the rules for negative exponents, which are important for this section. So if x is -1, 2 to the power -1 would look like what? 1 over 2 to the first power, which is 1 over 2. Now, everybody did get a packet back there. Even though it says 2.3, it's chapter 5 and chapter 6. That's why I put the packets back there. What is 2 to the power 0? What? 2 to the power 1 is 2. 2 to the power 2 is 4. If you picked up one last week, you don't have to pick up another one. So what do you notice about these numbers? As x gets bigger, they get bigger. As x gets smaller, they get smaller. The farther to the left, the lower it goes to 0. The farther to the right, it gets higher. That's this one. Now, if we had 1/2 to the power -2, again, we have a fraction, so we flip it and drop the negative and distribute. So it's 2 squared over 1 squared, which is 4 over 1, which is 4. So 1/2 to the power -1. The negative makes me flip 2 over 1, distribute, so it's 2 to the first, 1 to the first, which is 2 over 1, which is 2. One half to the 0 power is 1. 1/2 to the first power is 1/2. 1/2 to the second power is 1 squared over 2 squared, which is 1 over 4. So the bigger x becomes, the smaller y becomes. So it decreases. That's what happens. Let's do some graphing examples. Graph the following. F of x equals 2x minus 3. F of x equals 2x minus 4. F of x equals 5 minus 0.5x. Back to chapter 2 when we did transformations. So what's this first graph going to look like?
You know,
Is what? What do you mean to the right? What kind of shift do we have? Horizontal or vertical? Why? Because it happens to the x. The change happens to the x first. Whatever x I put in there, I have to subtract 3 first. So that makes it horizontal. I don't touch the f of x, the y value until I do all that stuff. So it's a horizontal shift. Which direction, how many spaces? 3 to the right. So I shift my origin to there. So there's my new origin. Everything else is the same. Here's 1. It shifts over here now. So that's where I cross the axis. The base is 2, so is it increasing or decreasing? It's increasing. So the graph looks like this. What's this one doing? What kind of shift is this one? Well, yeah, because that's horizontal. So this one has to be vertical because that's outside the function. So what does it do? Which direction? How many spaces? How many spaces? Down 4 spaces. So here's my origin. I drop down 4 spaces. 1, 2, 3, 4. So there's my new origin. Remember, it originally crosses once at one space above the origin. So my new intercept is there. And it's still an increasing function. That's what that looks like. And this one, what's going to happen here? What kind of transformations do we have here? Okay, that's one of those changes. Do it step by step. Let's look at this one. First off, what does the function look like?
it's gonna be
0.5x. What does that graph look like? It's decreasing. Why is it decreasing? It's between 0 and 1, right? Okay, so next thing that happens is outside of it. What does that negative make me do? Remember, if you change the value of x, you change horizontally. If you change the value of y, you change vertically. So what this one does is I flip over the x-axis. All these values that are positive, I now make them negative. So it now crosses through -1. If it's outside the function, it's a vertical shift. If it's inside the function, it's a horizontal shift. Okay, what else happens? We did this. We did this. What's the last thing that can happen? Go up, because it's positive 5, go up 5. So 1, 2, 3, 4, 5. There's my new horizontal asymptote. I mean, my new x-axis. So it shifts from here to here. Since my graph crosses 1 below that, there's my graph. So can we find the x-intercept? How? Well, what is it? How do we find the value of it? We know it's going to cross, yes, but what is the value? What is this x value? How do you find the x-intercept? What are the steps? Set y equals 0. So I set the whole equation equal to 0. Yeah, well, yeah, you're right. I moved 5, but since this is negative, I'd move that one over. So I have 0.5x equals 5. No, see, we haven't got that part yet. Because this is an exponent, we can't divide. We have to do something else. We have to do a conversion, which we haven't got to yet. But yeah, here we will change it to instead of exponential, we're going to change it to a logarithmic. We'll get to that point in a little bit. But yes, so far so good. This part we haven't, you'll see the conversion we do in the next sections or so. Here's an application problem. Compound interest. What is compound interest? Compound interest is what banks do when you borrow money from them. This is how often that they charge interest on the money that you borrowed from them. And here's the formula. This just tells you, using the compound interest, what's owed. You hear those commercials, let's say that um, if you have money coming to you, we'll pay you now, so you have to wait for it. That I have an annuity, and remember that commercial? I have an annuity and need cash now. That's what A stands for. That's an annuity. An annuity is, what is this note worth in the long run? Well, after everything's paid back to you, was, let's say you got in a car accident and you can't go to work for 6 months, and you get X number of dollars per month. Let's say $1,000 a month, but you need more money than that right now. So what you can do is you can sell me that $6,000 note. I'll pay you like $5,000 for it. You would get 5,000 for it, and I'll get more money back in 6 months. That's an annuity, is what the thing is worth at the end of the how much you have. So that note to you is worth $6,000 in 6 months, but you can't wait that long. You need the money now. So I'll give you $5,000. You give me your note, and I'll wait 6 months, and I'll get $6,000. So I will make $1,000. Yeah, but it's not that simple, because it's usually more than that. It goes, if it's worth a $2 million ones, I'll give you $400,000 for it, and at the end I'll get 2 million. You get 400,000 minus taxes and everything. You'll come up with 100,000, and it's very much a scam. It's very much a scam. But people, because they need money, they don't bother looking anywhere else. They just go straight to those places. If anybody who promises to give you money, when you see those people who said buy houses cheap, well, those are scams. You see those commercials say, we'll give you an offer for your house today. Legally, if I look at your house and say, I'll give you $10 for it, is that an offer? Yes. Is it a fair offer? No. That's not what they said. They never said a fair offer. So I'll give you an offer in one day. They'll make some low ball offer that you won't have time to go look at. Is it really worth that little? And they'll turn around and sell it for twice as much. So again, all those places are scams. Always, if you need money, ask and beg every place. I mean, go to community credit unions. Never go to a bank. Go to community credit unions. Go to your church. Go to your neighbors. Go to your friends and family. But you have to make sure you pay them people back, because if not, you just made tons of enemies, and life won't be happy for you. So they can't trust you anymore. Yeah, and then all of a sudden you just burned every bridge you have. So it's not a good thing. So that's an annuity. That's what the note is worth. P is called the principal. Principal. Principal is the amount borrowed. The annuity is the amount worth in the future. The principal is the amount you borrowed now. R is the rate in percent, but you have to convert it to decimals. When they say 5% APR, APR stands for what? Annual percentage rate. Or they don't use annual percentage rate. What they do is they'll give you something like quarterly, which means every 3 months they'll recalculate your debt, or monthly, or weekly, or daily. Your credit cards are calculated daily. Yeah, so every day you have money out from a credit card, you're paying money on it. N is the number of payments per year. That's it. If it's annual, it's one. If it's quarterly, it's 12. If it's monthly, quarterly is 4. I'm sorry. If it's monthly, it's 12. If it's weekly, it's 52, and so on and so forth. If it's daily, it's 365, and so on and so forth. And T is the time in years in which you borrow the money. For a car loan, usually they say it's 5 years, but now they figure out they make more money if they give you 7-year notes. And if you only keep it for 6 months, the time would be half. All right, so that's the formula to find the annuity, what a note is worth. So here's the example. Suppose $100,000 is invested at, they said, I'm going to say 10%. It makes it easier for us. Compounded semi annually me see what else. A. Find the function. Find the amount if t equals 0 and 4, and graph it. So, since we're looking at what this thing is worth in a future time period, it's an annuity. What is my P? Okay, I know it's principal. What is my P? 100,000. What is my N? What is my R? What is my T? Okay, that's in percent. I need it in decimals. What is in decimal? You want to put what? 0.1. Just move the decimal 2 to the left. What's my time?
Sim.
2 would be 2 years. This is half a year. It's half a year. And what's my no, that's not, that's N. N is half. It's semi. T is 0 and 4. We have 2 times. In other words, the 0 is when you borrow it, you pay it back the next day before any interest occurred. 4 is after 4 months. So we have $100,000. 1 plus 0.1 over 1/2. 1/2 times 0. Actually, I'll show you why it's easier than that, because at 0.1 divided by 1/2, it's a fraction over a fraction. It's 0.1 over 1. Flip the bottom, so it's 0.2. Instead of writing this, I can write 0.2. So I have $100,000. 1 plus 0.2, you have 1/2 times t. So this part here won't change. This part here won't change. But the only thing that will change is your time t. This is the only part that changes. Everything else, once you define it, it's set. It's set. So 1/2 times 0 is 0. Anything to the 0 power is 1. So it's $100,000 at t equals 0. Yeah, because you haven't kept it for anything, so it's worth what you borrowed, $100,000. Now, at t equals 4, we have $100,000 times 1.02, 1/2 times 4. 1/2 times 4 is 2. 1.02 to the power of 2. So I have 1.02 squared times $100,000. That note now, after 4 months or four whatever periods this is worth $104,040. So T is 4. So after 4 years, it's worth 104,000. There's only 1% interest. Now, if you really want to see what it tastes like today, your interest rates are in the 9, 10 up from there. What if your interest rate was 15%, which is 0.15? So we would have 100,000, 1 plus 0.15 over 1/2 to the power NT. 1 plus 0.3 to the power NT. 100,000, 1.3 NT. So let's change this to 2 like we did the last one. Let's see what happens here. So we have 1.3 squared times $100,000. So this is at 1%. This is at 15%. You've just paid 54,000 or $64,000 more, 65,000 in the same period of time, which is why I mean, never borrow money unless you definitely have to. All right. And if you do, pay it back ASAP. The number E. E is a constant that's used in mathematics. 2.7182818334, something like that. So it's a constant number, like pi. It's used in engineering, it's used in biology, it's used in the sciences to determine rates of growth and population growth and decay, how it grows and how it dies. It's a base number. And if you look at your calculator, if you look at the scientific calculator, you have log ln, and you'll always have an exponential function here. Exp is exponential. And you'll always have that in there. You always have those three. You're always going to have log, ln, and e to the power whatever. So what would this graph look like? Oh, it's an increase. Yeah, it's going to be increasing. It's the same as we did earlier. This is just base 2.718. What would this graph look like? What would that graph look like? What's that? Actually, it won't be. I'm sorry, it won't be a graph. It'll be a value. but the E graph looks the same. This is a value. So we have 2.7183. That's what this one would be. This one would be 2.718 to the power negative 0.023. Get this calculator again. So we have E is right here. Do that. Here's E. We click that. This button here, X to the Y. We just did X. We're now going to put the value of Y in there. That's the value. That's E to the power 3. What would E to the power 1 be? 2.18, it'd be what it is. What would E to the power 0 be? Be 1. Anything to the power 0 is 1. What would E to the power negative 0.23 negative? Where's my negative there? What do you think that would be? Think of the graph. Think of the graph. Where is negative 2 point or negative 0.23? X is right here. Here's negative 1. Here's negative 0.23. So it's going to be below 1. It's going to be smaller than 1. It's going to be how much smaller than 1? That much. Because E to the 0 was 1. And anything to the left of that, E to the negative numbers, will get smaller and smaller and smaller. E to the power negative 5. That's going to be pretty small. It is 0.00. Because the further I go to the left, the smaller the number becomes. All right. And graphing. What would this graph look like? Is it a horizontal or vertical shift? Which direction? How many spaces? 3 spaces to the left. So there's my new origin. There. And it crosses at 1. I just now move it over 3 spaces. What does E to the power negative 0.5x look like? No. That's the base. This is the exponent. The base is E. That's not changing. So we know what E to the x looks like. That looks like that. It crosses through 1. What is this telling me to do? Well, I divide it in half. Because I divided by it in half, it now grows a lot slower. Because remember, the closer we get to 1, the more horizontal it becomes. It becomes a lot shallower, yes. Now this negative tells me, and I've got to flip it across the y-axis. Remember what we did earlier when we had square root of x? That looks like that. When I changed it to negative x, it looks like this. Whenever you change the sign of x, you change the horizontal displacement for it. You flip it across the y-axis, right? So it becomes this one. So this one would look like this. It's very shallow though. And the last one, we have this x. This is 1 minus e to the power negative 2x. That's what I'm saying. We have this function here. So first off, we have e to the x. That looks like this. Then we have e to the power 2x, which means it grows a lot faster. Then we have e to the negative 2x. What does that negative do? Flip it across the y-axis. So this is e to the power negative 2x. What does the negative in front of the e do to it? It's vertical shift. Well, not really a shift. It's a what kind of vertical what? Instead of 1, it's now negative 1. It's a flip. It flips across the x-axis because I changed it from positive to negative. And then the 1 does what? It's positive 1, so it goes up 1 space. So it used to cross, here's the x-intercept. I go up 1 space. It's now there. My y-intercept is 1 down, so my y-intercept's there. So the graph looks like this. Here's my x-axis. 1 down from it is my y-intercept. All right. That's the end of that section. So that discusses exponentials. Now we're going to discuss logarithmic.